In this video, we're going to look at different types of reactions. In this one, we are going to focus on substitution reactions. So we're going to look at the chlorination of methane, esterification, and saponification. So substitution reaction is a chemical reaction in which an atom or group of atoms in a molecule is replaced by another atom or group of atoms. So one thing is being replaced by another. An example of this is a halogenation of an alkane, and in this case that we're going to be looking at, chlorine is our halogen and our alkane is methane, so Cl2 and CH4. Okay, so that's what we're going to be looking at in a moment. Then esterification, okay, an acid and an alcohol coming together to form an ester and water, and saponification would be what we looked at in the lab, making soap in the lab. So you have lard or olive oil with sodium hydroxide, creating soap and glycerol. So this is our chlorine mechanisms. We have an initiation stage, a propagation stage, and a termination stage, which we will look at in a moment in a little more detail, but if you want to pause the video and read down through this now, feel free to do so. In this mechanism, free radicals are used. Okay, so it's called free radical substitution. There are two forms of evidence for how we know that this happens. One is that small amounts of ethane are formed during the reaction and formed in the products. That can only be formed when two metal radicals bond together. So a metal radical being CH3 plus CH3, and that forms C2H6, which is your alkane. Also, if tetramethyl lead is added to the reaction mixture, the rate of reaction increases. So that gives more metal free radicals into the system, so it speeds up your propagation stage. To form those radicals, there are three ways to split a covalent bond, and only one of these actually forms radicals. If you split a covalent bond using unequal splitting, you produce ions. Okay, so here, if you had a bond between X and Y, in there you have two electrons. In heterolytic fission or heterolysis, the two electrons that are in that bond go with one or the other. Okay, so in this first example, both electrons go with your X, so your X becomes negatively charged while your Y is positively charged. In the second example here, both the electrons go with the Y, so that becomes negatively charged, so you have a negative ion, and your X then is your positive ion. If you were to split them equally though, you form radicals, so it's called homolysis or homolytic fission. So you have one electron with both. Okay, no charges associated with them, because the charges you're talking about here are relative to each other, and the charges of both of these are the exact same. So they're two relative to each other, there isn't really any charge. In order for that to happen, for that bond to be broken, you need to have some source of energy. Okay, that energy can come from heat or light, and in the example we're going to look at, UV light is used in order to form chlorine. So these are typical properties of some free radicals that you can read down through. Okay, so now we come on to the chlorination of methane. So you need UV light or sunlight, and heat can be used as an alternative energy source, but UV light is the most effective. We're going to focus mainly on this first one, which is the monochlorination of methane. Okay, so you have CH4, right, CH4 plus Cl2. Okay, one of these H's is replaced by a Cl molecule, so then you have CH3Cl and HCl, hydrochloric acid, formed. Okay, your free radicals are very reactive because they want to bond that unpaired electron. So that is the reason why free radicals are used in these reactions. That chloromethane can go on to react with a further chlorine molecule, and another hydrogen can be replaced, and so on until all the hydrogens have been replaced in tetrachloromethane. Okay, this is known as a chain reaction also. You would have heard of chain reactions before, and that is because once it starts, it gets faster as time goes on and keeps going. So this is our initiation stage. This is when our chlorine molecule has been broken down into two separate Cl molecules. So we start with Cl, bond it together, you apply UV light to it, and it breaks this bond. That bond is the one that is broken out of all the molecules we have, rather than the bonds between chlorine and hydrogen, or the hydrogen molecules together. It takes less energy to break the chlorine, so that is why that one is broken. It's the weakest bond, requires the least amount of energy to break it. So that is broken, and it forms these two chlorine free radicals, which then can go and are used to attack the methane molecule. This is our propagation stage. So you see here we have our chlorine free radical that we made in our initiation stage. This then attacks, we use the term attacks, this methane, and it goes on to bond with a hydrogen. So it takes a hydrogen off and it forms this methyl free radical, CH3. That CH3 can then go on and react with a chlorine, okay, that is broken, and the chlorine will go in there and bond its unpaired electron, and then this free radical is left over. So this is this free radical over here, and again it starts all over again. So it's a chain reaction. This is our termination stage then, where our reaction is going to finish up. These are all products. So this isn't one reaction after another. All of these are happening at the same time and terminating your reaction. Okay, so any chlorine free radicals that are left over can bond together and form Cl2 again. You have chlorine and CH3 making your chloromethane. Okay, and then your two methyl free radicals forming your alkane, and these are the diagrams for each of them down along. This is an overview of our chlorination of methane. And here is some piece of evidence for how we know that that is how the reaction takes place, that we know that that is the mechanism for it, some of which we'll come across already in this video. This is just an overview of what we went through there, just using diagrams. At the endpoint, okay, this chloromethane can go on and react with further chlorine free radicals, and another hydrogen may be replaced. So then you'd have dichloromethane, then you can go on and have you can have trichloromethane if that dichloromethane goes on and is in an environment where there are lots of these chlorine free radicals again. Another hydrogen can be substituted, and eventually you come to tetrachloromethane, where all of the hydrogens are replaced. But this doesn't always happen. Another example of a substitution reaction is esterification. So an ester is formed when an alcohol and a carboxylic acid react together. It can also be called a condensation reaction because water is formed as one of your products. So at the end you have an ester and you have water formed. It's also regarded as a substitution reaction because one of the H of your OH group in the carboxylic acid is replaced by an alkyl group. So an alkyl group is just a functional group in organic chemistry only consisting of carbons and hydrogens. So in this here we have our acid and we have our alcohol. So and forming an ester and water. So in this case we have ethanoic acid and ethanol, and we produce ethyl ethanoate and water. So ethyl ethanoate is an ester, and you have water formed as well. This happens in the presence of heat and concentrated sulfuric acid. So here, this is your OH group on your acid, on your carboxylic acid. That is replaced by your alkyl group, so that is this here. So that is what is substituted in instead of this H. The OH that's left over from your alcohol and that extra H from your acid is what forms your H2O, your water. Okay, this is just a bit more of an explanation of what happens. This happens in reflux when you're doing it in the lab. You need concentrated sulfuric acid as a dehydrating agent, as it removes water as it is formed, because the equilibrium causes the equilibrium to move to the right, and thus increases your yield of the ester. If you had a lot of this water at this side, it would cause the backwards reaction to occur, and it would reduce your yield of your ester. Okay, esters are fairly unreactive, but that doesn't make them useless. They're often used as flavorings. Okay, and this is how we would go about naming an ester, which you should already know about at this stage. Okay, so now we come on to hydrolysis of esters. So hydrolysis, we should know at this stage. Okay, hydrolysis, so lysis means cutting. To cut, hydro refers to water. Okay, so this hydrolysis of esters is when the ester reacts with the water and you come back to form your acid and your alcohol. So it's the reverse of esterification. Called hydrolysis because the water or the ester is reacting with water. And a similar reaction happens with the base. If you use a base here instead of the water, base such as NaOH or sodium hydroxide. Okay, that's what we would refer to as base hydrolysis of an ester. Okay, so this is your ester like we had in the last example, reacting with your water, and you're coming back to form your acid and alcohol again. Okay, if we use NaOH instead of your water, alright, you form a salt. Okay, so if you have an ester and a base, you form a salt and an alcohol rather than an acid and an alcohol. Okay, so this can be called base hydrolysis of an ester or saponification. We look at saponification in the lab. It's one of our mandatory experiments. Okay, and salts are long-chain potassium or sodium salts of carboxylic acids. So that is an example that we look at in more detail in the lab rather than here in theory. And that is our first type of organic reactions.